when I move the light away to the side of the bipolar cell, what I now get is something a little bit different. So originally my light was here. Now I'm going to shine my light slightly to the side, and what I get now is a different response altogether. I now actually get an inhibition. So what I can do now, so that's a bit odd, and what I find is I get the same response here. If I shine the light all the way around the outside like this, I get the same thing again. If I shine down here, I don't see anything. If I shine just around the outside, I get inhibition. If I put the light in the middle, I get an excitation. So that means I have got a receptive field that's kind of, I've got this middle bit like that where I get excitation, and I get this surround where I get inhibition like that. So we can redraw this and say that we've got an on center and an off surround. If I were to pick instead now of this, I did it with an off bipolar cell, I would get what I find is the exact mirror image opposite. Light in the middle, of course, it's called an off bipolar cell, so light directly in the middle is off, cause an inhibition, but on the outside now I get an excitation on the outside. Right, so response to light now would be for an on bipolar cell, I get excitation here and inhibition in the surround. For an off bipolar cell, I get inhibition here and excitation around here. So what is this all about? It's all about contrast. Because this is detecting changes. The reason I say that is because if I were to shine a light over the whole receptive field, the plus and the minus would actually cancel out. So in other words, a constant light over the whole thing wouldn't actually cause a response. It's only when it's light at one point and dark at another do I actually get a response in these bipolar cells. So that's why I say they're all about contrast. So that's now our third thing that we wanted to talk about, which is all about lateral inhibition and contrast. So what this does is if I imagine I put all my bipolar cells in a row like this, so these are all my bipolar cells, let's say they're all on bipolar cells. If I have a light, let's see what happens when we have an edge. Let's take the receptor fields one by one. Let's start off with neuron number 1. So here's its receptive field, positive, middle, and negative on the outside. So the light is on both of these areas, so they cancel out. So we get 0 for that one. Same with number 2, same with 3, same with 4. But what about number 5? Right, so number 5, how does the light fall on this receptive field? So let's take the one on the edge. The light is here. So we are now stimulating just the negative part. So that actually goes down. But number 6, now the light has moved across to here. So we're now fully stimulating the plus and only partly stimulating the negative. So remember, if the plus and negative cancel out, then having slightly less negative, the same amount of plus, means that we actually get a plus signal. 7, there's no stimulation, so that goes back down to 0. So can you see what's happened is we have got an edge detector. So these bipolar cell receptive fields are actually creating an edge detector. The next topic we need to look at is the retinal ganglion cells. So we are now looking, we've looked at the bipolar cells, you've done photoreceptors before, we looked at bipolar cells, now let's look at the retinal ganglion cells. These have a receptive field pretty much the same as the bipolar cells, but there's a difference. Some of them are big receptive field, and some of them have small receptive fields. These are called magnocellular, and these are called parvocellular. These are good for high resolution image. These are good for detecting movement because they've got a bigger field. But on top of that, so we got size of receptor field. We've also got 2 temporal contrast. What do I mean by that? So imagine that I'm recording from a retinal ganglion cell, and what I do is I switch the light on and off. So this is we're going to pick an on RGC. If I switch the light on, I see, now, these have action potentials. I see some cells will keep firing while the light's on. So that's a sustained response. But other cells will respire vigorously, but then stop firing during the response. So these are phasic. So we've got sustained responses and phasic responses. So in terms of getting a good quality image, you want a sustained response. If you want to detect movement, you want a phasic response. Going back to what we said about the receptive fields, we've now actually got 2 different sides of receptive fields and 2 dynamic characteristics. Each of these results in a map over the whole retina. So there's one map. If you look at all the magnocellular cells, they create a map of the retina like this. So those are the magnocellular ones. The parvocellular ones are doing the same thing. So you've actually got 2 maps superimposed. Plus, you've also got the different temporal maps as well. So actually what you've got is map upon map upon map. And these different maps are all going up to the brain. So you don't have one image going from the retina. In fact, you don't really have an image at all. You have contrast and motion images. You actually have several parallel maps at the same time. So, the last thing we need to talk about is horizontal and amacrine cells. These are horizontal cells and amacrine cells. The horizontal cells help to create the receptive fields of the bipolar cells. The amacrine cells help to create the more complicated receptive fields of the retinal ganglion cells. So that is the basic design of the circuitry of the retina.